surface reservoir. Okay, surface reservoir. The surface reservoir aims to maintain appropriate pressure to supply to the user. Okay. Now there may be numbers of the we call the loading. Then this is for example there was small user and big users. Okay. And then after and it has used the water, it will be collected, and the wastewater will be collected here. Okay. And then treated by the wastewater treatment works and discharged to natural water body. All right. Now to maintain for the water supply system, for most of the time, it will have a single way for the water supply. For example, for the very beginning supply system, the water source may be the water reservoir. Okay. But the water surface reservoir will directly serve the three users, okay, in one straight way. Okay, in one straight way. Now, this system is it's the most economic. Okay, it's the lowest cost to produce this kind of the supply. However, you can consider if there is some suddenly, okay, there is a blockage, or if there is a broken in the pipe here. If such situation, such accident happen, the user L1 and L2 will have no water supply, okay? Because this is only one-way supply for the user 1 and user 2, okay? So there may be, we know that the WSD will help to have the contingency plan to provide that the contingency water supply and try to connect the broken pipe as soon as possible. Okay. How about if there is a second route to connect this route and here, and there is a second route and to connect here. So this will make that even though that one of the pipe to be broken, okay, due to the repulsion, okay, or due to the running out of age, okay, so that the water supply is still reliable, okay. The water is still able to supply to the user 1, user 2, even though that this pipe has a blockage, or sometimes some of the pipe may need to under maintenance, okay, because you know that some of the pipe is running out of age, running for many years. That there will be many the settlements that inside the pipe that will increase that the head loss and also reduce the flow. Okay, sometimes they may need to consider to be replaced. Okay, and another situation is that here at a certain time there will be more estate or more users to be built in a developing area. So one source is not enough. Okay, one source is not enough, even though that we produce connection of the users. One source is not enough, making that the pressure drop. The pressure is small. Okay, so that you need to have additional source input. So that as time goes by for an urban area, for an urban supply system, you may have multiple water supply and multiple users. Okay, and the thing is, you will make that the network to be very complicated. Okay, the task is how do you know what is the actual flow running in the pipe in this situation. Okay. Now to deal with this situation, we know that this must be done by the computer. Okay, but the thing is how the computer works out the flow, okay, is based on one of the famous methods. It is the now to solve this discharge distribution in the pipe, we also follow two principles. The principle we also mentioned before. Once the continuity equation must be satisfied. Okay. We mentioned the principle 2 in the previous parallel system. Okay. Now in the junction, flow in discharge must be equal to the flow out discharge. Okay. Directly flow equal to the sum of the outflow. Okay. Sum of the inflow directly equal to the sum of outflow. This is the first principle. The second principle, same as the parallel system, the head loss between the two junctions must be the same. Okay. Now in L3, no matter how complicated the network system it is, okay, there must be the connection between the two junctions. Okay, so that the head loss between the two junctions must be the same. This is the second principle to be followed. So come to one single, we call the loop. Okay, we call the loop. One single loop. One loop. This is there is an enclosed loop and open loop. Okay. Now we look at this enclosed loop. Enclosed loop. Now in this enclosed loop, the flow will be flowing like this, this, and this. Okay. Now from A to B, B to C, and A is also from A to B and to C. Seems to be very complicated. We can simply classify or separate the pipes by using the clockwise and counterclockwise manner. Okay, we know that the clock running like this direction. Okay, so that if the clock running like this direction, right? So that in this loop, we focus on the flow of the pipes in the loop, related to loop. AB is clockwise or counterclockwise. AB flow is clockwise. Okay. BC is also clockwise because it flows like this pattern. Okay. So that the AB is clockwise, BC is clockwise. Okay. And but the AD, okay, it is like this way, so that the AD is counterclockwise. DC is also counterclockwise. Okay, so we use the clockwise and counterclockwise to separate no matter how many pipes. Okay, we can separate the pipes into two categories. One is clockwise pipes, and another one is counterclockwise pipes. Okay. Now, connected two junctions, that is A and C. Junction A and C. Okay. Connecting the junction A and C, there may be this pipe, and there may be this route. Okay, so that by separating the counterclockwise and the clockwise pipes, we simply divided the loop flow into the parallel system. Okay, one is flow like this, and another one is flow like this direction, counterclockwise. Another one is clockwise. Okay, so the head loss between the two junctions must be the same. The HLC is equal to the sum of HLCC, which is HLAD plus HLDC. Okay. So, so that this is the principle we follow for finding that the head loss calculation. Right? No matter how complicated it is, no matter there will be 5 pipes, 6 pipes, we just simply divide it into clockwise and counterclockwise. Right? Two manners of the flow. Alright, here the two head loss are the same. We use the KQ power 8 manner to calculate the head losses in the pipe. We can, because we will use the Darcy-Weisbach equation to find out this, so that the N is usually, we take the 2, okay? Here it has add the delta Q to the clockwise, the calibration factor. The calibration or the delta Q is the calibration factor for the discharge. It is add to the counterclockwise direction pipes and subtracted from the counterclockwise pipes. Okay. Now this delta Q after this change will be calculated by this equation. Okay, by this equation. So to determine the delta Q, if you will need to calculate the sum of the counterclockwise pipes, the clockwise pipes head loss, subtract the sum of the counterclockwise pipes head loss, and divided by the sum of NKQ power n subtract 1, and sum of the NKQCC power n subtract 1. Okay, to calculate this types of the manner to find out the delta Q. Once the delta Q is determined, you will add to the counterclockwise flow and subtract it from the clockwise flow. Seems that you may not understand what I'm talking about. Okay? Now, we will give you example. Now, 通常咧，嗱呢種嘅計數咧係複雜㗎啦。OK， 嗱咁我哋通常會係點咧？通常咧，你會譬如話攞到一個 network 咧，你要係做一個 initial assumption 嘅，因為 initial assumption 咧，你就要 assume 咧每條 pipe 嘅 flow 係幾多嘅，根據一啲已知嘅 information， 根據 overall 嘅 input 咧，你會根據埋個 continuity equation 咧去估算咧，做一個初步嘅估算。呢、個估算可以好誇張，可以甚至某一條 pipe 係冇 flow 都得嘅，唔緊要。咁你可以即係每條批咧即係都要合理嘅嚇，即係你都要係 fulfill 個 continuity equation 入嘅同埋出嘅一定要相等 ，OK？ 咁你可以呢度100，呢度0，呢邊 out 咧就呢度50，呢度50咁都得嚇。咁但係咧咁你做完一個 loop 嘅 assumption 之後咧，你就會計算咧呢度每條批嘅個 head loss， 根據你嘅 assumption。咁跟住咧入咗呢條式咧計到 delta Q。計咗 delta Q 之後咧，你就用第一次你就計算咗 delta Q 之後咧，你就會就下一步咧，你就會喺 counterclockwise 嘅 flow 入邊咧加翻上呢個 delta Q， 跟住 clockwise 嘅 flow 咧就減翻呢個 delta Q， 去修正翻佢嘅 discharge。咁呢個叫 correction discharge， 咁就係修正翻你頭先個 assumption。點為咁，然後跟住不斷咁樣修正完之後，再重複計數重複又重複咁樣計幾次，咁去到乜嘢情況下先至係完咧？就當佢嘅 delta Q 咧係好細嘅時候，即係佢話 fewer trial are required to solve the Qs approximately 0.6 of the computed delta Q is used 即係話佢嘅 delta Q 計出嚟咧。即係0.6嘅意思，即係去到4聲5入嘅一個標準啦。其實即係話，譬如話你個 delta Q 加上去佢每條批嘅 flow 嘅時候咧，佢4聲5入之後咧，唔會影響到上一次嗰個計數嘅。咁咧就叫 suppose 叫完㗎啦。不過喺電腦度咧，當然你可以，通常如果手計嘅話，你計你 loop 佢700次咧就差唔多啦。咁如果係電腦嘅話，你可以 loop 佢20次咁樣咧就好精準啦。OK， 咁所以就呢個嘅 Hardy-Cross method 咧，就係一個咁樣嘅即係一個make first assumption， 跟住再修正嘅方式嘅。OK。The next is the linear theory method. It is based on the Newton-Raphson method. Okay. This considers also the energy input and energy loss in the pipes. Okay. Now this method relies on the energy equation and also use the Newton's rough method. Okay, we will talk about this one next time. Okay, so so today we will just finish the Hardy-Cross method first. All right. So next we will talk about some tutorial question. Now, firstly, tutorial 1, question 2. We haven't finished yet. So for this question, it's related to the force exerted on the curved surface. Now, determine the hydrostatic force acting on the radial gate if the gate is 12 meters long, which is normal to the page. Show the line of action of the hydrostatic force exerted acting on the gate. Now, the radial gate is the kind of the device controlling the water levels in the reservoir. It is kinds of the reservoir's spillway. Spillway is a kind of the setup to maintain the water level in a healthy water level for the reservoir. Okay, the reservoir, you know that it is to maintain the water, right? Now, however, if the water level is over the desired level, that will have the risk to damage the reservoir. Okay, so that the spillway is important to control the reservoir's surface. Okay, so that some of the reservoir use the spillway, radial gate spillway. Okay, radial gate spillway. Just like this is. So this is not the radial gate spillway. Now this one is a radial gate spillway. Just like this. Now this radial gate spillway, all the force is pointed towards the hinge. Okay, so that it will compared to the previous spillway, that this radial gate spillway has benefits that it's easier to control. Okay, the force exerted to open and close the spillway. Okay, so that is very numbers of the reservoir prefers using this kind of spillway. Okay. Now here we are going to calculate how much is the hydrostatic force exerted on the spillway if the water overhead level is 15 meters and the spillway, the gate's radius is also 15 meters. Right? The 12 meters long is talking about the longitudinal length of this one. Okay. Now, for this kinds of the question, we will firstly work out the force diagram and the momentum diagram. Okay. For the for this kinds of the force exerted on the curved surface is not the momentum diagram. Okay, it's static force problem. We will cut. Okay, method 1. We will cut this water block out for study. Method 1 will cut this one. Okay, we'll cut this water block. method 1, we cut this one for the analysis. This is the water block we cut, okay? This one. In a three-dimensional view, it will be like this. Okay? It will be like this way. Now, we will analyze that what is the force exerted on this water block. One is the horizontal force, Fh. The other one is the vertical force, Fy. And also the self-weight. Okay? Because the upper surface is the water reservoir surface, so that there is no pressure force in considering the gauge pressure. Okay? So for the horizontal forces, it is Fh is this is a rectangle. Okay, rectangle. The rectangle's centroid is in halfway of the height. Okay, of the height. The height is 50 meter here and 12 meter here. Okay. So that the Fh is equal to the force is equal to the pressure. Centroid's pressure times the area. Okay, for the vertical plane. For the vertical plane, this one, okay, is equal to 1/2 of the 50 meter raw water, okay, G, 1/2 of the 50 meter. Calculate up to this point, and multiply by the area. Area is 12 meter times 50 meter, okay. Rho G of the water will take the 9810 Newton per cubic meter times 15/2. This is to find out the central pressure, okay? And times the area, 12 times 15. So the result is about 13 very long, okay? 13.243 meganewton, okay? Meganewton. Now the Fv vertical force is contributed by two things. Fy first, okay? Fy first. Fy is the bottom surface here, okay? Fy is the bottom surface here. It's upward pressure force. It's also calculated by the PC bottom times area. The pressure at the bottom is calculated the full height, which is calculated from the water surface to this level, okay, 50 meters height depth. Rho G times 15, okay? The bottom's area, this length is 12 meter, but this length is to be determined. This length is to be determined. We can look at here. Right? This radius is 50 meter. And this is 50 meter, okay? This is also 50 meter. So that we are finding that the maximum this distance, okay? This distance. We are finding this one. We say this is the x. We say this x. The x, here the x is supposed to be equal to, now this angle, because all the edges is 50 meter, so that is 60 degree and this is 30 degree, okay? 邊三個形。So x is equal to 50 meters subtract the 50 meter. Okay, this length subtract the 50 meter times the cosine 30 degree or the sine 60 degree. So supposed to be, is now x is calculated like this. So this area is equal to is 12 meter times x, so that it is equal to rho g times 50 meters times 12 times the 50 subtracts 50 times the cosine 30 degree. So it is 9810 times 50 times 12 times the so the result is calculated to be 3.549 meganewton. Okay, this is Fy. Another one is to calculate the self-weight. Self-weight is calculated by the this area. Okay, this area. This area can be contributed by the this rectangle. This is x. This is the height of 50 meter, and subtract the area of this one. Subtract the area of this shape. Okay, the area of this shape. This area can be counted by this is a geometric problem. Okay, subtract the fan shape. Subtract this the triangle area. Okay, so it will be calculated by this method. We may say this is the A1, A2, and A3. In the model answer, I use different thing. Okay. You may have the okay. So use A1, A2, and A3. So this is maybe use an A4. Okay, A4. Maybe A4 is calculated by the A1, which is the A1 subtracts the A2 subtracts A3. And A1 it is calculated by the 50 meter times the x. Okay. And the A2 is calculated fan shape because this this angle is 60 degree. Okay. This whole angle is 60 degree. Okay. So the radius is 50 meter. It's a pi times 50 meters squared times 60 over 360, and subtract the triangle shape. Subtract the triangle shape. It will be equal to the 50 meter times the 50 meter cosine 30 degree and times 1 over 2. It will be like this. A3 is here, okay? A2 is this one, okay? A1 is this one. So that this is to find out this area, A4, okay? To find out this area. If you have a better method, okay, you can tell me. This is the method that we have. So it will finally calculate it to be equal to the 9.82 meters squared. Okay, 9.82 meters squared. This area, okay, is 9.82 meters squared. Is that okay? Now, the area is determined, so after that, we will calculate the self-weight. It will be equal to the rho G of water times the length of the gate, okay, is 12 meter times the area A4, okay. It will be equal to 9810 times 12 meters long times the A4's area, 9.82 meters squared, and this is finally calculated to be the result of 1.156 meganewton. Okay, this is pointing downward. The Fy is pointing upward. Okay, W is pointing downward, the self-weight is pointing downward. The vertical force is finally the Fy subtract W, which is 3.4549 subtract the 1.156 resulted in 2.3923 meganewton. It is that force is pointing upward. So the resultant force Fr is equal to the horizontal force, which was calculated to be 30.23244 3 meganewton. I had plus 2.393 meganewton J hat. Okay. For the line of action, because it must point towards the center, okay, so that we may calculate the tangent alpha of the Fv over the Fh. It is equal to 2.933 93 over the 13.243. It is equal to 0.18. So the alpha is calculated to be this arctangent 0.18. It is 10.24 degree. Okay, so the force of action in this situation is like this. Okay, this angle is 10.24 degree. Okay, this angle is 10.24 degree. This is method one. Method one seems to be very complicated, especially calculating the cell weight. Okay. Now method two will be simpler. Method two will be simpler. Okay. Method two, we may consider that this will be the horizontal force is the same, but the vertical force, we may consider that this is to replace the this void volume has been replaced by the air. Okay, it's supposed to be water, but now replaced by the air. So it is contributed as the buoyant force. Okay, is contributed by buoyant force. So the Fv is equal to the buoyant force here. The buoyant force is equal to the rho times g times the area here. This area is equal to, similar to the previous A2 subtract A3 times the long times the length. Okay? A2 subtract A3 times 12 meter. Alright? A2 subtract A3 is A2 subtract A3 is to find out this this shape. Okay? So it's 9810 times the A2, which is pi times 50 meter square times 6 over 360. Subtract the triangle area. 50 times 50 times the cosine 30 degree and times 1 over 2 and times 12. The result of this calculation is also calculated to be 2.393 meganewton. Okay. So the buoyant force must be pointing upward, so that it will have a very faster way for the calculation of the vertical force in this situation. Okay. So that's for if you can see. Okay, you can identify that this area has been considered to be the buoyant force. You can save the steps for calculating the vertical force. Okay. Now this is the main difference for the method 1 and method 2. It is the difference of calculating the vertical force. So maybe for the question 2, we have just talked about the question 2 in this tutorial tonight. Okay. So係啦，嗱，咁因為我哋 哋計算呢個嘅，因為佢係睇緊係啦，我哋係睇緊呢個嘅面嘅。
你話講確切，你話記住咗1/3嗰個。
佢唔係啊嗱，1/3係個 action point 嘅。我哋計個 pressure 嘅話咧，就係計個 centroid， 個 centroid。OK， 我哋睇翻呢個。
即係睇翻嗰個面個 centroid。
係啦，佢係一個長方形，長方形嘅 centroid咧就係高度1倍。咁所以我哋計個 pressure 嘅時候咧，計到 centroid pressure 咧就係計到個高度1倍。所以呢度嘅 rho g 乘翻15/2咧，就係計緊個 pressure 嘅，計緊個 centroid 呢一點嘅 pressure。咁然後跟住咧個 pressure 乘翻佢呢個側面嘅呢個 area 咧，就係12×10。
即係如果假設上面嗰個，譬如話你水大咁嘅樣啦，佢嗰度有個位咁樣凹咗入去，即係上邊12喺個凹咗入去，我就揾翻呢一個面個 centroid。
係啦。
即係 in 即係嗰個 centroid 嗰條方條欄換翻落去，跟住再計翻佢個 pressure 咯。
係啦，如果你係即係你可能係講緊係咪呢種情況，即係譬如話你個水壩係咁樣嘅，即係
譬如我呢個面凹咗啲喺度啊，咁樣。咁我呢個面咪就係呢個應該係咁嘅，個 centroid 應該再入啲。
咁佢係淨係睇呢個面喎，因為你界嗰個，你睇界嗰個 block 咧，呢個企嘅呢個面咧就係一個長方形嘅，佢同你呢度冇關係嘅。你如果你話個 water block 係咁樣嘅話，即係你意思係咁啦，即係你嘅意思就係講緊你個 water block 如果係咁嘅話，即係你嘅意思就話呢個面，即係呢個面嘅嗰個 central 可能有面埋嘅嘛。
唔係入指方向嗰個面咯，入指方向頂嗰個面，即係呢個位啊。
即係呢個位唔係一條直線咯，即係佢呢個位係可能凹入去咯。
因為我哋界嘅就係好似一把刀咁樣打直打橫。
即係好多時候都係一個方形個機咁樣。
係啦，即係我哋通常即係如果係用呢種方法，我哋咁樣解嘅。咁同埋呢一個，同埋呢度呢一個嘅 radio 機佢亦都係一個即係咁樣嘅形狀屈曲嘅。咁譬如話咧，你講嘅情況有可能咧，譬如話我哋都試過咧，譬如話佢係一粒佢係一粒嗰啲釘咁嘅形狀嘅，因為可能佢有不規則嘅一個形狀。
係，佢一個面咪
譬如話佢係一粒釘咁樣啦，即係喺塊板度嘅一粒釘咁樣啦。咁我哋界嘅時候咧，就係要界一個咁樣嘅圍住佢咁嘅形狀。如果係 method 1，如果係呢個 method 嘅話，咁佢呢個水平壓過去呢個面咧，都係一個正方形或者長方形。
咦？咁呢個位睇都係咩嘅喎？都係攞最加一半嘅喎。
佢最主要嘅 difference 咧，就係佢計個 volume 嘅時候，計呢個 liquid block 嘅 volume 嘅時候咧嘅麻煩嘅地方就係，你要將呢個嘅長方體扣減咗佢入面嗰個實體。
咁我一定計波陣時咁樣計。係
啦，即係呢啲情況就計波陣時咧就會。
但係咁我呢度我計翻個 horizontal force 都係
計
一半嘅喎。
都係計到一半嘅呢個位。你可能佢個水面係就到呢度嘅，但係你就計到呢度啦。
OK。
Method 2就主要咧就係、你就考慮佢 replace 咗幾多水嘅，所以佢就係呢一個嘅 volume 呢個 area 乘翻個長度咯，即係呢個 area 即係我哋頭先嘅計嘅嗰個線形面積減去呢個等於3個形嘅面積，再乘翻個長度12b，咁計翻呢個 volume，再乘翻個 density 包括之類嗰啲數嘅。即係我都建議你係用即係呢個簡單嘅方法嘅。如果 翻轉又唔同喎 ，OK？ 如果調翻轉係咁樣去箍住啲水咧，如果佢咁樣箍住啲水咧，如果佢咁樣箍住咧，咁咧你就都係用 method one 你就計呢一個嘅，你就計 method one 嘅呢一個去計咧就唔易嘅。
有冇邊啲情況咧？嗰、個嘅 horizontal force 唔係攞一半？
有。如果佢呢個形狀，如果呢個 liquid block 唔係一個正方形嘅，譬如話佢呢塊板，佢依家呢個係一個三角形嘅一個釘咁樣啦，即係如果係個三角形嘅釘，即係咁你個 liquid block， 即係如果佢係個三角形咁樣嘅話，你個 liquid block 咧你就唔係一半喎，咁你就係高度嘅三分之，即係由上計落嚟咧係高度嘅三分之二個 percent 即係如果你計嗰個 liquid block 係咁樣嘅話，
但係咁如果 in this case 嘅話，我計個正方形唔係更加方便喎？
咁其實都係好少會咁其實好少會即係你計嘅時候都係盡量計到自己方便計數嗰啲嘢，因為你如果計一個咁樣嘅三角形嘅 liquid block 出嚟咧，呢啲面咧嗰個 pressure 咧就好奇怪，就好難計，就好難計啲啦咁樣。咁所以通常計都係計一個四方方嘅形狀嗰種分析。
OK。
想問下，頭先教咗一啲譬如包燒嘅機構編程，咁但係咧，我計點講咧？佢話有唔同嘅詞，同一個情況啦，可能用唔同 equation 會有唔同答案咯。到時點樣去計？
咁我哋都會係講俾你聽主要方法去計嘅，即係一般情況下都係大多數都係打 Series equation 去計嘅，咁即係有啲當然即係話，如果譬如話個題目俾嘅係Hayes-Williams equation 嘅 coefficient 或者 Rayleigh equation coefficient， 咁你就係用嗰啲 equation 去計咯。咁我通常都會講清楚呢一條 question 咧用邊種方式去計嘅。
咁如果應用上咧，即係平時日常工作會話特登，我會特登揀邊題，係純粹睇佢複雜程度，定係睇？
其實呢樣嘢就係睇你個 assumption 嘅。你用 DW equation 又得，用HW equation 又得咁就睇你 assumption 同埋睇你有啲咩 information。咁有啲時候你用 Darcy-Weisman equation 嚟 assume 咗個定咗嘅 fictional factor， 都可以用啲Darcy-Weisman equation 去計。咁如果你係用 open channel 嗰啲咧，基本上都係用 Rayleigh equation 多。但係如果係 water pipe 嘅話咧，就 Darcy-Weisman equation 或者係 Hayes-Williams equation 都會用嘅。Hayes-Williams equation 咧就佢淨係睇 material 㗎啦，咁就唔使睇 Reynolds number 嗰啲嘅。咁所以有啲時候